Let's build, from the ground up, a masterclass in what our quantum computers are actually doing. Not the textbook fairy tale, the real machines, the real jobs we submitted, the real numbers that came back. I want to understand the whole mechanism, end to end.
Good. And we have the perfect material to do it with, because you didn't just read about this, you ran it. You put a black hole on a superconducting chip in Poughkeepsie and on a trap of ytterbium ions in Maryland, and you have the counts to show for it. So every abstract idea I introduce, I'm going to nail to one of your actual runs, H01, H02, X06, H08. By the end, you should be able to trace a single number, like 0.987, all the way back to a laser pulse or a microwave tone.
Perfect. So start at the absolute bottom. What is a qubit, really? I know the slogan, superposition, 0 and 1 at the same time, but I want the mechanism.
Right, let's kill the slogan and keep the physics. A classical bit is a switch. It's 0 or it's 1. A qubit is a two-level quantum system, and its state is a vector, a direction, in a two-dimensional complex space. We write a general state as alpha times ket 0 plus beta times ket 1, where alpha and beta are complex numbers called amplitudes.
Amplitudes, not probabilities.
That's the crux. Alpha and beta are amplitudes. The probability of measuring 0 is the magnitude of alpha, squared. The probability of measuring 1 is the magnitude of beta squared. And because those are the only two outcomes, the magnitude of alpha squared plus the magnitude of beta squared has to equal 1. That's the normalization condition. The state is a unit vector.
So, both at once really means the vector is pointing somewhere in between.
Exactly. Superposition is not secretly 0 or 1, and we don't know which. It's a genuine third thing, a definite quantum state that happens to be a blend. And here's the part that has no classical picture. The amplitudes can be negative or complex. Two states can have the same probabilities, but different phases, and that phase is physical. It shows up the moment those amplitudes interfere. Interference of amplitudes is the entire engine of quantum computing. Everything we do is arrange for the wrong answer's amplitudes to cancel and the right answer's amplitude to add up.
Hold that thought on interference, because I know it's coming back in our echo experiment. But first, one qubit is a vector in 2 dimensions. What happens when I have 10 qubits, like in our black hole chain?
This is where it stops being cute and starts being powerful. 2 qubits don't live in 2 plus 2 dimensions. They live in 2 times 2, 4 dimensions. Ket 00, Ket 01, Ket 10, Ket 11, each with its own amplitude. 10 qubits live in 2 to the 10th dimensions. That's 1024 complex amplitudes describing one state of the system.
1024 numbers for 10 qubits.
For 10. For your H01 chain, that's the full state vector. Now push to 50 qubits, that's 2 to the 50th amplitudes, about a quadrillion. At 300 qubits, you have more amplitudes than there are atoms in the observable universe. You physically cannot write that vector down on any classical machine. But a 300-qubit quantum register just holds it. The state lives in the hardware. That exponential is the whole reason we care.
And that exponential is exactly the wall I keep hitting with exact diagonalization. When I do the classical version of these black hole sims, I build the Hamiltonian as a matrix and I diagonalize it.
Right, and let's be precise about what you do classically, because the contrast is the whole point. In your exact diag code, the many-body Hamiltonian in the E05 run, you literally build a 2 to the 10 by 2 to the 10 matrix, 1024 by 1024. You form it out of Pauli operators with Kronecker products. You call A to diagonalize it, and then you can compute anything. The exact echo, the exact occupation, to 15 decimal places. You have the whole wave function in your hands, every amplitude, and you can read any of them whenever you like.
Which is exactly what a quantum computer will not let me do.
That's the trade, and it's the single most important thing to internalize. On the quantum computer, you also have all 1024 amplitudes, physically, in the 10 qubits. But you cannot read them. You are allowed exactly one operation to extract information, Measurement. And measurement is brutal. When you measure 10 qubits, the superposition collapses and you get back one bit string. 10 classical bits, like 10011000000. One outcome, that's it. The rich complex vector becomes 10 ordinary bits.
So which bit string do I get?
One is drawn at random, and the probability of each bit string is the magnitude squared of its amplitude. That's the Born rule, the deepest and most annoying fact in quantum mechanics. If a bit string had amplitude with magnitude 1/3, you'd see it about 1/9 of the time. You never see the amplitude itself. You see samples drawn according to the amplitude squared.
So a single run of the machine tells me almost nothing.
A single run tells you one sample from a distribution you can't otherwise see. That's why we don't run once. We run the identical circuit thousands of times, and each run is called a shot. In H01, you took 4,096 shots per circuit. Each shot, prepare the state, evolve it, measure, record 10 bits. Do that 4,096 times, and you build up a histogram. How many times did 1000 came up? How many times 0100, and so on? That histogram, normalized, is your estimate of the Born rule probabilities. The quantum computer is, at its heart, a sampling machine. You program a probability distribution into amplitudes, and you sample it.
That reframes everything. The output of my black hole simulation isn't a wave function, it's a pile of bit string counts.
A pile of counts, from which you reconstruct exactly the physics you wanted. And the beautiful thing about your experiments is that the physics quantity, the occupation on a site, the survival probability of a state, is directly a probability, so counting bit strings is measuring physics. We'll get concrete on that. But let me close the loop on the basic mechanism first. How do we manipulate the state between preparation and measurement? That's gates.
Yes, gates. I write X, I write a 2-qubit gate. What is a gate physically doing to the vector?
A gate is a rotation of the state vector. Mathematically, every quantum gate is a unitary matrix, unitary meaning it preserves length, so a unit vector stays a unit vector, probabilities stay adding to 1. An X gate on 1 qubit is the matrix that swaps the 0 and 1 amplitudes. It's the quantum knot. In H01, your very first instruction is QC.X on qubit 0. That flips qubit 0 from ket 0 to ket 1, putting the single excitation on site 1. That's you preparing the initial state, ket 1 0 0 0 0 0 0 0 0 0, the excitation sitting inside the horizon.
So state preparation is just a gate too.
Everything is gates. Preparation, evolution, the kick, even the basis change before measurement, all unitary gates, all rotations of that big vector. A single qubit gate rotates within 1 qubit's little sphere. The interesting ones are 2-qubit gates, because those are what create entanglement.
Define entanglement for me mechanically, not mystically.
Mechanically, a 2-qubit state is entangled if you cannot write it as 1 qubit state times the other qubit state. Take the state ket01 plus ket10 normalized, one excitation shared between 2 sites. There is no way to factor that into qubit A is in some state and qubit B is in some state. The 2 qubits only have a joint description. Measure one and you instantly know the other. That non-factorizability is entanglement, and it's generated by 2-qubit gates. Your hopping gate, the one that moves the excitation from site to site, is exactly an entangling gate, because it takes ket10 and rotates it partly into ket01. Superposition across 2 sites of where is the particle is an entangled state.
And that's the resource. Okay, I feel like I have the primitives now. Amplitudes, superposition, unitary gates, entanglement, Born rule sampling by shots. Let's turn our actual physics into a program. I have a black hole chain Hamiltonian. Walk me from that to a circuit.
Let's do it carefully, because this map, from a Hamiltonian to a gate sequence, is the intellectual core of the whole project. Start with what you want physically. You have the 10-site chain from Shy and collaborators. The Hamiltonian is a sum over the bonds between neighboring sites. Written out, H equals the sum over sites J of kappa sub J times, in parentheses, x sub j plus 1 plus y sub j plus 1 all over 2.
Spell out what those pieces mean.
X sub j and y sub j are Pauli operators acting on qubit j. The combination xx plus yy divided by 2 is the hopping term. It takes an excitation on site j and moves it to site j plus 1 and vice versa. It's the quantum version of the particle can walk left or right. Kappa sub j is the coupling strength on that bond, how easily the particle hops across it. And the whole black hole trick is in how kappa varies along the chain.
Right, the couplings encode the curved spacetime.
Precisely. In the curved profile, kappa sub j equals the hyperbolic tangent of, in parentheses, j minus 3 plus 1/2, times eta sub d, divided by 4 times eta sub d, with eta sub d equal to 0.35. What that formula does, the coupling goes nearly to 0 at the bond between site 3 and site 4, that's the horizon, and saturates to a constant far away. A particle approaching the horizon bond finds the hopping strength dying to nothing, so it slows down and never quite crosses. Exactly like light near a real event horizon. The geometry of spacetime has become the pattern of hopping strengths on your chain. That's the physical idea you're encoding.
So I have H, but H is a Hamiltonian, a static operator. How does time evolution become gates?
The Schrödinger equation says the state at time ti is e to the minus iht applied to the initial state. That operator, e to the minus iht, is the time evolution operator, usually called u of t. It is unitary. Good, gates are unitary, so in principle, simulate the black hole for time, t, means apply the single unitary u of t. The problem is that u of t is a 1024 by 1024 matrix. There's no native hardware gate that is the whole black hole for 2 seconds. We have to build u of t out of the small gates the machine actually has, 1 and 2 qubit gates. That's where trotterization comes in.
Trotterization. This is the step I want to really understand because it's in every one of my runs.
Here's the idea, and it's clever. The reason we can't just exponentiate h directly is that h is a sum of many terms, one per bond, and those terms don't commute. The xx plus yy on bond 1 and the xx plus yy on bond 2 share qubit 2, so they interfere. E to the minus I times the sum is not the product of the individual exponentials. But, and this is the trotter insight, if you take a small enough time step, they almost are. The error in swapping the sum for the product shrinks with the step size.
So I slice time into little steps.
You slice the total time t into n small steps of size tau. Over one tiny step, you approximate e to the minus ih tau as the product of the individual bond exponentials. Do bond 1 for a little bit, then bond 2 for a little bit, then bond 3, and so on. Each of those individual bond exponentials, e to the minus I kappa tau times the xx plus yy over 2, is a 2-qubit gate, and then you repeat that little step and times to build up the full evolution to time t.
And in the code, that little bond exponential is literally one gate call.
It is, and this is a lovely concrete moment. In your build circuit function, you call xx plus yy gate with argument 2 times kappa times tau. That single Qiskit gate is exactly e to the minus I kappa tau times the xx plus yy over 2. You even verify it. The stage verify function builds that gate, builds the matrix exponential from SIPI directly, and checks they agree to better than 1 part in 10 to the 12th. That's the discipline I love in your code. You never trust that the gate means what you think. You numerically confirm the convention before a single shot is spent.
There's also this second-order business. Odd bonds, even bonds, half steps. What's that?
That's a refinement to make the trotter error smaller for the same number of gates. You split the bonds into 2 groups, odd bonds, 1, 3, 5, 7, 9, and even bonds, 2, 4, 6, 8. Within a group, the terms all commute because they don't share qubits, so applying a whole group at once is exact. The approximation is only in the ordering between groups. The second order or leapfrog scheme is, do the odd group for half a step, then alternate even for a full step and odd for a full step, and finish with odd for a half step. That palindrome structure makes the leading error cancel, so the error scales like the step size squared rather than the step size. In your code, that's the layer odd, layer even, layer odd pattern with the dt over 2 half steps at the ends.
And you fix the step to 0.5.
dt equals 0.5, so the number of trotter steps n is just t divided by 0.5. At time t equals 10, that's 20 steps. And here's the thing that will matter enormously later. More steps means more gates, means more depth, means more chances for the hardware to make an error. You verify that with dt of 0.5, the trotter approximation still matches exact diagonalization to better than 1 part in 100 across all your times. So the algorithmic error is under control. The hardware error is a separate beast we'll get to.
Good. Now, one thing I glossed, I've been saying the excitation on a site as if a site is a qubit. Is that automatic?
It's a choice, and it has a name, Jordan-Wigner. Your chain is really a chain of fermionic modes. A site is either empty or occupied by a particle. Jordan-Wigner is the dictionary that maps one lattice site to one qubit. Site empty is qubit in ket 0. Site occupied is qubit in ket 1. The occupation operator n sub j is the site full. Maps to 1 minus z sub j over 2, where z is the Pauli z. And the hopping term, the fermion moving from one site to the next, maps to that xx plus yy over 2. So one site equals one qubit is Jordan-Wigner in the single particle nearest neighbor case, where the messy non-local strings that Jordan-Wigner sometimes produces happen to cancel out.
In H01 and H02, the strings vanish, but in the interacting run, H08, there's an extra term. Show me how that becomes gates, because it's a different kind.
This is the interacting horizon Hamiltonian, and it's the richest circuit you built. On top of the hopping, you add an interaction. V times the sum over bonds of n sub j times n sub j plus 1, with V equal to 2. Physically, that's an energy penalty when two particles sit on neighboring sites, a repulsion. Now, n sub j is 1 minus z sub j over 2, so n sub j times n sub j plus 1, when you multiply it out, is a constant, plus a term in z sub j, plus a term in z sub j plus 1, plus a term in z sub j times z sub j plus 1, all over 4.
So the interaction becomes single qubit z rotations plus a 2-qubit zz term.
Exactly right, and that's exactly how your intr function builds it. For each bond, it applies an rz rotation of minus v tau over 2 on qubit j, another rz of minus v tau over 2 on qubit j plus 1. Those are the single z pieces, and then an rzz gate of plus v tau over 2 on the pair. That's the z times z piece. The rzz gate is e to the minus I times angle times z over 2. It's the entangling piece of the interaction. The constant piece is just a global phase and you drop it. And notice, because the diagonal z-type terms all commute with each other, a whole interaction layer is exact, no trotter error within it. All the trotter error lives in the hopping.
Let me make sure I have the full H08 circuit as a sequence. Prepare, evolve, kick, reverse, measure.
That's the anatomy, and it's worth walking slowly because it's an echo, a very clever construction. Step 1, prepare. You put 2 excitations down, on qubits 2 and 3, which are sites 3 and 4. That pair straddles the horizon bond. Step 2, evolve forward. Apply U of t as a trotter sequence of hopping and interaction layers. Step 3, the kick. Apply a single Z gate on the kick site, qubit 3, right on the horizon. Step 4, evolve backward. Apply U of t dagger, the inverse of the whole forward evolution, run for real on the hardware. Step 5, measure all qubits.
Why run time backward on the actual machine? That doubles the depth.
It does, and that's the honest cost, which you flag explicitly in the code. The reason is that this is an out-of-time order correlator, an OTOC, the standard probe of quantum scrambling and the butterfly effect. The observable is F echo, defined as the magnitude squared of the quantity bra psi 0, U dagger, Z on the kick site, U ket psi 0. In words, evolve forward, Poke the system with a Z at one location, evolve backward, and ask how much of the original state survived. If nothing scrambled, the forward and backward perfectly undo each other, except for the poke, and you get almost everything back, F echo near 1. If the poke's influence has spread, if the butterfly's wing beat has propagated, then the backward evolution can't undo it, and F echo drops.
And there's a slick identity that makes F echo trivial to read.
In the single excitation case, yes. Z on the kick site acting in that sector is 1 minus 2 times the projector onto the kick site. Grinding it through, F echo equals, in parentheses, 1 minus 2 times P sub S, quantity squared, where P sub S is the probability that the excitation reached the kick site during the forward evolution. So the interferometric echo is just measuring how much amplitude arrived at the butterfly site. Curved geometry should suppress that, the horizon blocks the front, so echo stays near 1. Flat geometry lets the front through, echo dips. That's the whole physics story in one number, and your stage verify confirms the identity holds to one part in 10 to the 12th on the actual trotter circuits before you spend a cent.
Beautiful. Now, the machines. I've run this on 3 completely different physical platforms. Superconducting at IBM, superconducting at Rigetti, trapped ions at IonQ. Start with the superconducting Transmon, because that's IBM Fez, my H01 machine.
A transmon is, physically, a tiny electrical circuit, an inductor and a capacitor, an LC oscillator, printed on a chip. An ordinary LC oscillator has evenly spaced energy levels, which is useless for a qubit because you couldn't address just 2 of them. So you make it nonlinear by inserting a Josephson junction, which is a sliver of insulator between 2 superconductors. The junction acts as a nonlinear inductor, and that makes the energy levels unequally spaced. Now the gap between level 0 and level 1 is different from the gap between level 1 and level 2, and you can drive just the 0 to 1 transition. Those 2 levels are your qubit.
And you operate it cold.
Rociously cold, around 10 to 20 millikelvin in a dilution refrigerator, because the energy scale of the qubit corresponds to microwave frequencies, 4 to 8 gigahertz, and you need the thermal noise well below that, or the qubit randomly jumps. Single qubit gates are microwave pulses at that frequency. You shine a precisely shaped microwave tone, and it rotates the qubit. 2-qubit gates on IBM's Heron chips use a mechanism called cross-resonance, or a tunable coupler, to switch on an interaction between neighbors. On Heron, the native 2-qubit gate is a controlled Z, or an echoed cross-resonance, ECR.
What's the catch with transmons? Because there's always a catch.
2 catches, and they define your whole experience. First, coherence. A transmon holds its quantum state for only about 100 microseconds on a big processor before it decays. That's the T1 and T2 times. Compared to atoms or ions, that's short. So your gates have to be fast, tens of nanoseconds, and your circuit has to finish before the state rots. Second, connectivity. The qubits are wired in a fixed lattice on the chip. IBM uses a pattern called heavy hex, where each qubit connects to only 2 or 3 neighbors. If your algorithm needs 2 distant qubits to interact, the hardware physically can't do it directly. It has to shuttle the quantum information over using swap gates.
And swaps cost me.
Every swap is 3 2-qubit gates, and every 2-qubit gate is your dominant error source. So routing on a fixed lattice inflates your gate count, which inflates your error. Now you got lucky, or rather you designed around it, in the black hole chain. Your Hamiltonian is a one-dimensional chain. Site 1 talks to Site 2, talks to Site 3. A line, and a line embeds perfectly into heavy hex. You just pick 10 qubits that form a path. So H01 on IBM Fez needed essentially 0 swap overhead. The nearest neighbor structure of your physics matched the hardware's connectivity. That is not an accident you should take for granted.
Now contrast the trapped ion, IonQ Fort 1, my H06, X06, and H08 machine.
Completely different physics, same abstract qubit. Here, a qubit is a single atom, an ytterbium ion, held in place by electromagnetic fields in a vacuum chamber, at room temperature, no dilution fridge. The two levels are two internal electronic or hyperfine states of the ion, and they are astonishingly stable. An idle ion can hold its state for seconds to minutes, versus 100 microseconds for a transmon. That's a factor of 10,000 or more in coherence.
So why doesn't everyone just use ions?
Because they're slower, and building big traps is hard. But for us, the killer feature is connectivity. Single-qubit gates are laser or microwave pulses on individual ions. Two-qubit gates work through the ion's shared motion. All the ions in the trap sit in a line and vibrate together like beads on a spring. And you use a laser to couple two chosen ions through that shared vibration, the Milmer-Sørensen interaction. The native gates are called GPI, GPI2, and MS. The point is, because every ion shares the same motional modes, any ion can be coupled directly to any other ion. All-to-all connectivity. No lattice, no routing, no swaps.
And that's the reason ion Q suited the interacting run.
That's exactly the reason. Think about H08, the interacting horizon. Jordan Wegener in the interacting case, and generally when your terms aren't strictly nearest neighbor, produces operators that act on strings of qubits, and the ZZ interaction couples specific pairs. On a fixed lattice, you'd pay swap after swap to bring the right qubits together. On Fort 1, all-to-all means the compiler places each 2-qubit gate directly, zero routing inflation. In your H06 notes, you can see it plainly. The logical 2-qubit gate counts, 82, 172, 226, 298, are the native compilation target, no routing added. The circuit that hits the hardware is as lean as the algorithm allows. For circuits whose interaction graph isn't a simple line, all-to-all is a genuine, countable advantage.
Now the number I keep seeing quoted, 99-point-something% 2-qubit fidelity. What does that actually mean, and why should I care so much?
It means when the machine applies one 2-qubit gate, it does the right rotation with probability about 99.9%. And with probability about 1 in 1,000, it does something wrong. A little over-rotation, a bit of the state leaking away, a phase error. One gate at 99.9% sounds fantastic. The problem is that errors compound multiplicatively over the depth of the circuit.
Show me the arithmetic, because this is the thing that bit me.
Let's make it concrete with H08. Your deepest circuit has 388 native 2-qubit gates. Suppose each 2-qubit gate has fidelity 99%, a reasonable full system figure. The probability that the whole circuit is clean is roughly 99% raised to the 388th power. 99% to the 388th is about 2%. 2%. So 98% of your shots have at least one error somewhere in that circuit.
2% of the signal survives. That's catastrophic.
And even if the gates were 99.5%, better than most full systems, 99.5% to the 388th is about 14%. Still most of your signal gone. This is the exponential decay of fidelity with depth, and it is the central antagonist of everything you're doing on today's hardware. It is why the number of 2-qubit gates in a circuit is the single most important number to track. Not qubit count, gate depth. You annotate it on every one of your quality figures, and you're right to.
Okay, so I have the physics, I have a circuit, I have a machine. Walk me through what actually happens when I hit submit. Start from my Qiskit circuit object.
Step 1 is transpilation, and it's the step people underestimate. Your circuit is written in abstract gates, an XX plus YY gate, an RZZ, a Z. The hardware does not have those gates. It has its own small native set. For IBM Heron, single-qubit rotations plus ECR or controlled Z. For IonQ, GPI, GPI2, and MS, which the bracket layer exposes to you as RX, RY, RZ, and CX. Transpilation rewrites your abstract circuit into an exactly equivalent circuit using only native gates, mapped onto specific physical qubits, respecting the connectivity.
And in the code, that's the transpile call with optimization level 3.
Right. Optimization level 3 is the most aggressive. It cancels redundant gates, fuses rotations, and finds a good qubit layout. You pass a fixed seed, 42, so the compilation is reproducible. Same circuit in, same circuit out, every time. And critically, after transpiling, you count the 2-qubit gates and the depth, and you print them, because that's your predictor of how badly the hardware will maul the result. In H01, the shallowest circuits are a handful of gates. In H08, the deepest is those 388.
Now the gotcha. Tell the barrier story, because that was a real bug that cost me.
This is a wonderful lesson in the gap between the simulator accepts it and the hardware accepts it. In the echo circuits, you insert a barrier, a Qiskit instruction that says, "Do not optimize across this line," on either side of the Z-kick. You need it, because otherwise the transpiler is too clever. It sees the forward evolution and the backward evolution, and outside the kick's light cone, it cancels mirrored gate pairs against each other, collapsing your honest 2 times depth echo into something shallower. The barrier forces the compiler to keep the real full-depth echo, so the machine actually does the work.
But then the barrier itself blew up on ion Q.
On ion Q through bracket, yes. The barrier does its job during transpilation, but a barrier is not a physical operation. It's a compiler directive. IBM's stack quietly drops it before execution. Bracket and ion Q do not. They see barrier in the instruction list, don't recognize it as a gate, and reject the entire task with a validation exception. So your fix, visible in the TOE-native function in the E05 run, is to transpile with the barrier present, so it still gates the optimizer and then explicitly strip the barriers afterward with the remove barriers pass before shipping to bracket. The gate sequence is already scheduled at that point, so removing the now inert markers changes nothing physical. You get the honest depth and a circuit the device accepts. That is exactly the kind of platform-specific papercut that only shows up on real hardware.
Then it goes to the cloud. How does submission differ between IBM and ion Q?
2 different provider stacks. For IBM, you use Qiskit runtime. You instantiate a sampler v2 bound to the back end, and you call run with your list of circuits and your shot count. Notice you send all 16 H01 circuits in a single job, curved and flat, all 8 times, 1 submission. That's deliberate. 1 job means 1 calibration snapshot, 1 Q weight, 1 consistent set of conditions across all your data points. For ion Q, you go through AWS bracket. You build a device object from the device ARN, that big string ARN:AWS: bracket pointing at the Fort 1 QPU in US East 1, and you call device.run per circuit. Bracket returns a task with an ARN UPOL.
And there's a queue.
There's always a queue. These are shared machines with 1 physical instance each. Your job sits in line behind everyone else's. For IBM, you pick the least busy backend that has at least 10 qubits. That's the least busy call in stage submit. For ion Q, you also check device status is online and that you're inside its execution window, because Fort 1 isn't always available. It runs in scheduled windows. Your submit code refuses to send if the device isn't online. When your turn comes, the machine runs your circuit for all the shots, then hands back the counts.
Let's nail the concept of a shot precisely, because it ties back to sampling.
A shot is 1 complete execution of the circuit, followed by 1 measurement. Prepare the qubits in the ground state, apply your whole gate sequence, then read out every qubit and record the bit string. That's 1 shot, 1 bit string. Then the machine resets and does it again. Same circuit, fresh run, for the next shot. 4096 shots gives you 4096 bit strings, which you tally into a histogram. Because measurement is random per the Born rule, you need many shots to estimate the underlying probabilities well.
How many is enough? How does shot count set my error bars?
This is just the statistics of counting. If the true probability of some outcome is p, and you take n shots, the number of times you see it follows a binomial distribution. Your estimate of p has a standard error of the square root of pa times 1 minus p divided by n. So the error bar shrinks like 1 over the square root of the number of shots. To halve your error, you need 4 times the shots. That square root scaling is exactly the formula in your analyze stages. You compute the error bar as the square root of pa times 1 minus p over the number of retained shots. For a probability near 1/2 at 4,000 shots, that's an error bar of about 0.8%. Perfectly good.
And on Ion Q, I can't just crank the shots because shots cost money.
This is the part textbooks never mention and your code takes dead seriously. Ion Q Fort 1 on bracket costs 30 cents per task plus 8 cents per shot. 8 cents per shot. So 1,000 shots is $80.30 for one circuit. In X06, you ran 4 circuits at 1,000 shots each. 4 times $80. 30 is $321.20. In H08, you ran 12 circuits, and to stay under a hard cap of $322, you solved for the maximum uniform shot count. 331 shots. 12 times in parentheses, 30 cents plus 331 times 8 cents equals $321.36. 332 shots would have tipped over the cap.
So the error bar and the budget are the same conversation.
They're the identical conversation, and it changes your experimental design. On IBM, shots are effectively free, so you take 4,096 and your statistical error is tiny. On IonQ, every shot is 8 cents, so you take 331, and your binomial error bar is correspondingly about 3.5 times larger. Square root of 4,000 over 331 is about 3.5. That larger error bar is the price of the trapped ion venue, and it's why your IonQ contrasts have plus or minus values around plus or minus 0.03, while your IBM ones are tighter. The budget guard in your submit stage isn't bureaucracy. It's a physics experiment design constraint.
All right, the job finishes, I fetch. Now I have raw counts. Walk me through turning bit strings into physics. This is where I actually get a number I can believe or not.
Let's start with H01 because it's the cleanest. You fetch, and for each of the 16 circuits, you get a histogram, a dictionary mapping 10-bit strings to how many times each appeared out of 4,096 shots. Now physically, your system has exactly one excitation. Number is conserved, the hopping term moves the particle, but never creates or destroys it. So the only bit strings that are physically legal are the ones with exactly 1 1, 1 0 0 0 0 0 0, 0 0 0, 0 1 0 0 0 0 0, 0 0 0, and so on. 10 legal strings, 1 per site.
But the hardware gives me illegal strings too.
Constantly. Because of errors, you'll see strings with 0 1s, or 2 1s, or 3. Those are impossible under the true physics. They're pure error. So you post-select. You throw away every shot that isn't in the single excitation sector, and keep only the physically legal ones. That's the post-select function. It keeps bit strings whose count of ones is exactly 1, and tallies which site that one landed on. The site probabilities P sub j are then the kept counts, normalized over the kept total.
This is error mitigation without any modeling.
It's the cheapest, most honest form of error mitigation there is. You're using a known symmetry of your Hamiltonian particle number conservation as a filter. Any shot that violates the symmetry is discarded as corrupted. You don't correct it, you don't model the noise, you just drop it. And you report how many survived, the retained fraction. In H01 at the deepest time, you retained about 11.5% for curved, 15.8% for flat. So at that depth, roughly 85 to 90% of your shots had a detectable error and got thrown out. The 11% that survive are clean, and from them you reconstruct the site populations.
And then the fidelity number, 0.987. Where does that come from exactly?
You compare the post-selected hardware distribution to the exact diagonalization ground truth. For each circuit, you have P hardware, the 10 site probabilities from the kept shots, and P exact, the 10 site probabilities from your classical SciPy calculation. The classical fidelity is the sum over sites of the square root of P hardware times P exact. That's the Bhattacharya overlap of two probability distributions. It's 1 if they're identical, less than 1 otherwise. Your median across all 16 H01 points was 0.987. That means, after post-selection, the hardware's black hole walk agreed with exact theory to within about 1.33% on median. On a real superconducting chip, running a curved space-time quantum walk, that's an excellent result.
Let me push on median, because it hides the depth story.
Good instinct, and this is where it gets honest. .987 is the median, the typical point, but fidelity is not uniform. It degrades with depth. Look at H06 on IonQ. The median post-selected fidelity was .747, but at the shallowest depth, 82 2-qubit gates, it was .987 for curved and .990 for flat. Nearly perfect at shallow depth. Then it falls off a cliff as depth grows, dropping to as low as .26 at the deepest points. The median averages over that range, so whenever you see a single fidelity number, your next question should always be, at what depth? A shallow depth fidelity and a deep depth fidelity are different physics.
Now, the echo observable F echo, that's a different reduction. How do counts become F echo?
Two ways, and you compute both, which I admire. The first is the raw survival probability. You defined the target bit string as the initial state, and you just count what fraction of all shots came back as that exact bit string. No post-selection, because the echo observable is a survival probability. The raw number is meaningful on its own. It's literally how often did the state return to where it started. The second is the post-selected version. Restrict to the single excitation sector, then read off the probability on the source site. You record both, and their agreement or disagreement tells you about the error structure.
And in the interacting H08, F echo is read even more directly.
There, it's especially clean, because your initial state is a computational basis state, 2 excitations on specific qubits. So F echo is just the probability that a full measurement returns that exact initial bit string. No post-selection needed at all. You count the shots equal to ket psi 0, divide by total shots, and that's F echo directly. The F from counts function does exactly that. It checks which qubits are occupied in each bit string and asks whether that set equals the initial occupied set. Clean and assumption-free.
X06 is different again. No post-selection, dual rail. Walk me through that reduction, because it's the cosmological particle creation one.
X06 is a 4-qubit circuit in a dual-rail encoding, simulating particles created by an expanding universe. The observable is the particle number per mode, n, and by the encoding it equals the probability of measuring the bit string 1010 plus the probability of measuring 0110. So you just read those two bins out of the raw 4-qubit histogram, add them, and that's n. No symmetry filter. The dual-rail structure means the amplitude you want is read directly, and the result tracked the exact quantum field theory prediction across the whole expansion rate curve. The ideal n at the fastest expansion is about 0.12, and the hardware traced the floor rise saturation S-curve as the expansion rate swept.
There's a subtlety I want you to flag there, the fake particle floor.
Yes, and it's a gorgeous example of reading hardware honestly. At the slowest expansion, the true particle number is essentially 0. The universe barely expands, no particles created. But the circuit at that point is still full depth. The gates are all there, they just conspire to near identity. So any gate error manufactures particles that shouldn't exist. In your noise study, the fake particle floor was about 0.044, where the true value is 0. That's not a failure. It's a measurement of the gate noise floor, and it reproduces exactly the overestimation the original paper saw on their hardware at small expansion. Knowing that your 0 reads as 0.044 tells you the noise floor of the whole apparatus. That's information, not embarrassment.
This brings me to the interpretation section, which is really what I care about most. How do I read these numbers honestly? Start with the ground truth discipline.
The bedrock is that for every one of these systems, you have an exact classical answer, because they're small, 10 qubits, 1024 dimensions, well within exact diagonalization. So you always know the right answer before you look at the hardware. That's your ground truth. The hardware run is not discovering new physics here. It's being validated against physics you already computed exactly. That's the correct posture for the current era. You're characterizing the machine as much as the physics. When the hardware agrees to 0.987, you've shown the machine can faithfully carry that computation. When it doesn't, you've mapped where it breaks.
And decoherence is the thing that makes it break. Give me the depth wall in H08 with the actual numbers, because that's the story I want to really understand.
This is the most instructive result in your whole project, precisely because it's a partial failure honestly reported. The goal of H08 was to see the interaction signature, the difference the repulsion V makes to scrambling near the horizon. Exact diagonalization says that at time 2, the curved interacting echo should be about 0.644. Your hardware at that point, the deepest circuit, 388 2-qubit gates, read 0.033. 0.644 expected, 0.03 measured. The signal was almost entirely washed out.
And that lines up exactly with the fidelity arithmetic you did earlier.
Exactly with it. 99% to the 388th is about 2%, and the echo collapsed to a couple of percent. The decoherence didn't distort the signal, it erased it. Every deep point tells the same story. At time 1, curved interacting exact is 0.71, hardware reads 0.25. At time 1.5, exact 0.61, hardware 0.09. The hardware values decay towards 0 as depth climbs, tracking the fidelity decay, not the physics. That's the depth wall. Beyond a few hundred 2-qubit gates on this machine, the answer is noise.
But you didn't just declare failure. There's a consistency check that saves the interpretation.
This is the part I want you to be proud of. The interaction requires depth. The V=2 circuits are the deep ones. But you also ran V=0 controls, which are shallower for the same time. And you can ask, at a shallow point where you should be able to see the signal, do you? At time 2, with V=0, the circuit is 164 gates, shallow enough. Exact says the curved minus flat contrast there is plus 0.039. Hardware reads plus 0.030, plus or minus 0.013. Those agree, so the machine is working correctly. The problem is specifically that the interacting signal lives at a depth the machine can't reach. That's the difference between the hardware is broken and the hardware ran out of coherence before the physics we wanted appeared. One is a bug, the other is a characterized limit.
And at the shallowest depth, you did see the horizon effect.
You did, faintly. At time 1, the curved minus flat contrast came in at plus 0.057, plus or minus 0.032. That's the right sign. Curved above flat, the horizon suppressing the front as predicted. At about 1.8 sigma. But it's 4 to 5 times attenuated from the ideal value of about plus 0.2. So you can honestly say the sign is there at the shallowest depth, weakly. The interaction signature itself is not resolved. The result is decoherence limited and inconclusive. Not a falsification of the physics, but a statement about the machine. That precision of claim is everything.
I want to talk about that word, blind. The memory keeps hammering blind analysis, no goal-seeking. What does it mean operationally here?
It means you fix your entire analysis pipeline. The post-selection rule, the observable definition, the error bars. Before you look at the hardware numbers, and you do not tune anything to make the answer come out right. The temptation on noisy hardware is enormous. You see 0.03 where you wanted 0.64, and you're tempted to apply some correction factor that scales it back up to where theory says it should be. That is goal-seeking, and it's poison. It manufactures the answer you already believed. The honest move is what you did. Report 0.033, note it's consistent with the decoherence flaw, and conclude inconclusive. A blind analysis lets the machine tell you the truth, including the truth that it couldn't do the job. If you'd goal-sought, you'd have confirmed the physics and learned nothing.
There's a physics-motivated correction that is legitimate, though post-selection. Why isn't that goal-seeking?
Sharp question, and the distinction is exactly the right one to hold. Post-selection is legitimate because it's committed before you see the data, and it's justified by a symmetry that's true independent of the answer. Number conservation is a fact about the Hamiltonian. Discarding number-violating shots removes shots you know are corrupted, regardless of what the surviving distribution turns out to be. You're not nudging the answer toward a target. You're removing events a symmetry forbids. Contrast that with looking at a washed-out echo and multiplying by some factor to undo decoherence tuned so the output matches theory. That's chosen after seeing the data to hit a known target. The test is, did you decide the correction before or after seeing the answer? And is it justified by physics or by the desired result? Post-selection passes, a fitted rescaling fails.
Cross-platform agreement. You keep bringing up that the same circuit ran on IBM, Rigetti and IonQ. Why does that matter for validity?
Because the three machines fail in completely different ways. IBM's transmons decohere via one physical mechanism on a heavy hex lattice with ECR gates. Rigetti's transmons are a different chip, different fab, different calibration. IonQ's ions are an entirely different modality, different noise, all-to-all laser gates. If you run the identical logical circuit on all three, and they agree with each other and with exact theory, then the agreement can't be an artifact of one machine's quirks. A coincidence that reproduces across three unrelated error models is almost certainly real physics. In H06, you note exactly this. The same logical circuits gave median post-selected fidelity 0.987 on IBM Fez, 0.749 on Rigetti Cepheus, and 0.747 on IonQ Fort 1. And at shallow depth, all of them hit 0.98 to 0.99. The physics is platform independent. Only the decay rate differs. That triangulation is a validity argument you can't get from any single machine.
Which raises the big question hanging over all of this. When does a quantum computer actually beat my classical exact diag, and when doesn't it? Because right now, honestly, my laptop wins.
Right now, for these 10-site systems, your laptop wins decisively, and you should say so plainly. Exact diagonalization of a 1024-dimensional matrix is instant and exact to machine precision. The quantum hardware is slower, noisier, costs $300 a run, and agrees only up to some fidelity. So for 10 qubits, the classical machine is strictly better. The value of your hardware runs at this size is not to beat the classical computer. It's to validate that the quantum machine can do the computation at all, to characterize its limits, and to build and debug the exact pipeline you'll need at larger sizes.
So where's the crossover?
The crossover is set by that exponential we started with. Exact diagonalization needs to store the state vector, 2 to the n complex numbers. At about 40 qubits, that's a terabyte. At 50, a petabyte. Beyond that, classical exact simulation is simply impossible, no matter how big your computer. A quantum computer with 50 or 60 good qubits and low enough error just holds that state in hardware. So the crossover is somewhere north of 40 or 50 qubits, but with a giant caveat.
The caveat being depth.
The caveat being depth, and it's the whole game. Having 50 qubits does you no good if your circuit needs 1,000 2-qubit gates, and your fidelity is 99%, because 99% to the 1,000th power is essentially zero. You'd measure pure noise, like your 388-gate wall, but far worse. So quantum advantage for simulation requires two things at once: enough qubits that classical exact methods choke, and low enough error over enough depth that the answer survives. Today's machines have the qubits but not yet the depth. That's precisely the wall you mapped in H08. You found the exact frontier where coherence runs out, on a real device with real numbers. That map is worth more than a hollow success.
And there's a middle ground, classical methods that aren't exact diagonalization.
A crucial one. Between exact diagonalization and quantum hardware sit clever approximate classical methods, tensor networks, matrix product states, that handle far more than 50 qubits as long as the entanglement stays low. Many black hole and horizon problems don't generate much entanglement, so a tensor network eats them for breakfast on a laptop, well past where exact diagonalization dies. So the real quantum advantage target isn't just big, it's big and highly entangled and deep, where both exact diagonalization and tensor networks fail, but a good quantum computer wouldn't. Scrambling physics, the OTOCs you're building, is one of the few genuinely hard regimes, because scrambling is precisely the rapid growth of entanglement that kills tensor networks. That's why your echo experiments are pointed at exactly the right physics for eventual advantage.
Let me make sure I can retrace the entire path myself. Take H02, the OTOC echo on IBM, and go from Hamiltonian to a single believable number.
Let's do the whole chain, no gaps. Physics, the 10-site chain, curved couplings kappa sub j equal to hyperbolic tangent of j minus 3 plus 1/2 times 0.35 over 4 times 0.35, horizon after site 3. You want the butterfly front, launch an excitation on site 1, inside the horizon, and watch whether it reaches site 6, outside. Observable, F echo equals, in parentheses, 1 minus 2 times P sub 6 squared.
Step 2. The circuit.
Prepare, X gate on qubit 0, putting the excitation on site 1. Forward evolve, second order trotter of e to the minus IHT with dt of 0.5, built from XX plus YY gates of 2 kappa tau on odd then even then odd bonds. Kick, a Z gate on qubit 5, which is site 6. Backward evolve, the inverse of the entire forward trotter sequence, run for real. Barriers around the kick so the compiler doesn't cancel the mirror. Measure all 10 qubits, that's 12 such circuits, curved and flat, 6 times each.
Step 3. Submit and run.
Transpile all 12 to IBM Fez's native gates, optimization level 3, seed 42, the deepest transpiles to around 602 qubit gates. Bundle into one sampler V2 job, 4,096 shots each. It queues, it runs, you fetch 12 histograms of 10-bit strings.
Step 4. Counts to number.
2 reductions, raw survival, fraction of shots that came back as the initial bit string, that's F echo directly. Post-selected, keep single excitation shots, read the probability on site 1. Compute the binomial error bar as square root of f times 1 minus f over the shots. And compare against the exact continuum echo you computed from sector matrices and against the trotter state vector, 3 curves, 1 data point on the same axis.
Step 5. Interpretation.
At shallow times, the post-selected echo sits right on the exact curve. Curved staying near 1, the horizon holding the front back, flat dipping as the front crosses. At deep times, depth eats it, and the echo decays toward the noise floor exactly as the fidelity arithmetic predicts. You read the shallow points as physics confirmed, the deep points as decoherence characterized, and you never ever rescale the deep points to make them look better. That's the whole loop. Hamiltonian, trotter, transpile, shots, post-select, compare, interpret honestly.
One thing we haven't dwelt on, why does the same physics quantity sometimes need post-selection and sometimes not?
It comes down to whether your observable is a probability of a specific bit string or a distribution over many. When the observable is probability of returning to one specific computational basis state, like F echo in H08 or N in the dual rail X06, you read that one bin directly. Errors just scatter counts out of it, and there's nothing to filter, though the count you get is attenuated. When the observable is a distribution over sites, like the walk populations P sub j in H01, you want to clean the whole distribution, and number conservation gives you a symmetry to post-select on. The choice isn't arbitrary. It follows from the shape of the observable and whether you have a symmetry to exploit.
And post-selection has a cost I should name.
The retained fraction is your budget. When you keep only 11% of 4,096 shots, your effective statistics are only about 450 shots, so your error bars grow accordingly. And there's a deeper danger at extreme depth. If you retain only 1 or 2%, like the 2 or 3 surviving shots at the deepest ion Q points in H06, post-selection can lie to you because the few survivors aren't guaranteed representative. An error can leave you in the legal sector by coincidence. So post-selection is powerful, but not free. It costs statistics, and at very low yield, you must distrust it. You flag that in the notes correctly.
Let me zoom back out. If I had to state in one breath what a quantum computer is doing when it runs my black hole sim, what's the sentence?
Here's the sentence. It encodes your 10-site chain into 10 physical 2-level quantum systems. It uses precisely timed microwave or laser pulses to apply a sequence of unitary gates that implement, step by tiny trotter step, the time evolution e to the minus IHT. Those gates weave the 10 qubits into a giant entangled superposition whose 1,024 amplitudes it never reveals. And then it measures, collapsing that superposition to one 10-bit string sampled with Born rule probability. repeating thousands of times so that the histogram of strings reconstructs the physics you asked for. The machine is an analog of your system, built from qubits, driven by pulses, read by sampling.
And the whole art is keeping the amplitudes intact long enough.
That's the entire game. Every amplitude you carefully sculpted with gates is under continuous assault from decoherence, and each 2-qubit gate is both a tool and a wound. It does necessary physics and injects about 1% of error. Your job as the experimenter is to design the shallowest circuit that still contains the physics. Choose the platform whose connectivity matches your interaction graph so you don't pay swap tax. Spend your shots where the error bars matter. Post-select on the symmetries you know, and interpret against exact ground truth without ever flinching from a washed-out result. You've done all 5 of those things across H01 through H08. That's not playing with a quantum computer. That's operating one as an instrument.
Let me test the connectivity point one more time, concretely. If I had to run H08 on IBM's heavy hex instead of IonQ's all-to-all, what specifically changes?
Concretely, the interacting circuit has ZZ terms on every bond and a trotter structure that, in the fully interacting case, wants specific pairs coupled that aren't all nearest neighbor after compilation. On all-to-all Fort 1, the compiler places each of those 2-qubit gates directly. Your native counts were 82 up to 388, and that's the raw algorithmic cost, nothing added. On heavy hex, any coupling between qubits that aren't physically adjacent needs swap networks to bring them together, and each swap is 3 more 2-qubit gates. For a circuit already near the coherence wall at 388 gates, adding swap overhead could push it to 500 or 600, and by the fidelity arithmetic, 99% to the 600th is a fraction of a percent. The signal would be even deader. So the all-to-all choice for H08 wasn't aesthetic. It was the difference between a circuit that's merely decoherence limited and one that's hopelessly so.
Even though the trapped ions are individually slower and the shots cost 8 cents each.
Even so, you paid $321 and larger error bars to get 0 routing overhead and world-class coherence per gate. For a deep, awkwardly connected circuit, that's the right trade. For H01, a simple nearest neighbor line that embeds perfectly into heavy hex with no swaps, IBM was the right venue, and free shots let you take 4,096 of them and drive the statistical error to nothing. Matching the machine to the circuit's structure and depth is a real design decision, and you made a different, defensible call each time. That's the mark of understanding the hardware rather than just using it.
One last thread, the verification discipline in the code. Every run has this exact then verify then dry run sequence before a single dollar is spent. Why is that architecture the right one?
Because on a quantum computer, you get one honest shot at spending your budget, and a bug looks exactly like decoherence. If your bit ordering convention is wrong, or your gate has the wrong sign, or your Jordan-Wigner map is flipped, the hardware will happily return numbers that are wrong, and they'll look like noise, and you'll blame the machine. So you build a firewall of classical checks. Stage exact, compute the ground truth in NumPy or CP. Stage verify, confirm your gate conventions, match the exact operators to one part in 10 to the 12th, and that the trotter circuit matches exact evolution to under 1%. That catches sign and convention bugs. Stage dry run. Run the exact submit-ready circuit on a local classical simulator and confirm the sampled counts reproduce the state vector. That catches bit ordering and transpilation bugs. Only when all 3 pass, and only with explicit human approval, does the paid submit fire. By the time a photon or a microwave pulse touches your circuit, everything except the hardware noise has already been proven correct. So when the answer disagrees, you know it's the machine, not you.
Which is exactly what lets you read the depth wall as physics and not as a bug.
That's the payoff. When H08 came back at 0.033 against an exact 0.644, you could state with confidence it was decoherence and not a coding error, because the identical circuit reproduced the state vector on the simulator to shot noise precision the day before. The verification firewall is what converts a disappointing number into a trustworthy scientific statement. The machine ran out of coherence at this depth, full stop. Without that firewall, you'd never know whether you'd discovered a limit of the hardware or just a limit of your own debugging.
I think I actually have the whole mechanism now, from an amplitude I can never see, through trotter slices and native gates, onto a specific chip or ion trap, through the cue and the shots, back to a histogram, filtered by a symmetry compared to exact truth, and read without flinching. That's the masterclass I wanted.
And notice you can now hold both facts at once, which most people can't. Fact 1, for 10 qubits your laptop still wins, and these runs are validations and characterizations, not victories. Fact 2, the exact same circuits, made a bit bigger and a lot deeper, are pointed straight at the one regime, deep scrambling, high entanglement, where classical simulation must eventually fail and a coherent enough quantum computer would not. You've built the instrument, calibrated it against truth, and mapped exactly where it breaks. The day the hardware's depth catches up to its qubit count, you already know precisely which circuit to run and how to read the number it gives back. That's the whole point of doing it honestly now.
On that note, the machine holds the state it can never show us. We sample it into existence 1,000 times over, and we only ever believe it because we already knew the answer. Let's end there. Thank you. This was exactly the ground-up build I needed.
Anytime, go run the next one, and keep spending the verify stages before the shots. The physics will still be there when the coherence catches up.